Let's look at the limit of a sequence, and with the goal of getting to the careful, rigorous, standard mathematical definition. But we're going to start out with some examples. I want to motivate this about why would we come up with what might look like a complicated definition. So the first one, a sub n, is just 1/2, 1/4, 1/8, 1/16. Or if this is term number 1, this is term number 2, etc., then the formula is simply a sub n is 1 over 2 to the n, or if you like, negative exponents 2 to the minus n. Very simple sequence of numbers. And a cool thing you can do with any sequence, and especially with this one, is not just put commas in between, but actually look and turn it into a summation. Look at the sum of all these terms. So we'll call that s sub n. So s sub n is going to be, start out with 1/2, then 1/2 plus 1/4, then 1/2 plus 1/4 plus 1/8, etc. Or in other words, s sub n is 1/2 plus 1/4 plus, and then it's going to go to, let's see, so this is the third one, we ended up with 1 over 2 to the n, 1 over 2 to the 3, so in general it's going to be 1 over 2 to the n. Now you might see this with like plus ones and minus ones in a lot of cases. You might see this one starting with 1 instead of 1/2. Very standard example, but there's not a big difference. Okay. So that's going to be the summation. Let's see what are these numbers actually. Okay. It's 1/2, 3/4, 7/8. It turns out to be 15/16, etc. Okay. So I'm going to be talking about these sequences quite a bit. And I want to give you two pictures. The point is to get something where we're very rigorous and it's going to be more algebraic looking, about logic and algebra, not pictures. But we always want a picture to have some intuition. Just don't mistake it for a proof in itself. So picture number 1 for a sub n is going to be a number line picture. Let's say 0 and there's 1. And we'll just draw dots on a number line to indicate where everything is. So a sub 1 is here, a sub 2 is here, a sub 3 is here, a sub 4. And as you get 1 over 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/28, they cluster in here. They're all positive, but they seem to be getting very, very small. They seem to be approaching 0. So maybe is that the limit of the sequence? And indeed it will be. Okay. Picture 1 for s sub n. Okay, so remember the first one was 1/2. It starts here. But then we're going to go to the right. We're going to take 1/2 plus 1/4. That's 3/4. We did that calculation a minute ago. 1/2 plus 1/4 plus 1/8 is up here. 1/2 plus 1/4 plus 1/8. And one observation you might have seen, if you've seen this sequence at all before, is that you have 1/2 plus 1/4. That plus 1/4 exactly went half of the remaining distance to 1. And then if you add 1/8 to that, to get this guy, well, this guy was a 1/4 away from 1, and you add 1/8 to that. And now you're 1/8 away from 1, and guess what? You add 1/16 to get to this one. You've gone half the distance to get to S4. And what you get is things that certainly look like they're approaching 1. So is this the limit of the S sub n's? Okay. We'd like to be able to say yes and say precisely what that means and prove it based on a careful definition. Picture number 2, always useful as well for sequences, is to picture it like a function. In that first picture, I just had a number line just for the values of the sequence, not the indices. And here's where you take a sub n and you sort of treat it like an f of n, input and output. And so here's the n axis, and here's like the a sub n or the s sub n axis. Excuse me, 1, 2, 3, 4, 5, 6, 7. And so for a sub n, for example, say this is 1, then the first value is 1/2, then 1/4, then 1/8, then 1/16, then 1/32. And you get a bunch of dots that as you go to the right, as you explicitly increase the index, they get really, really small. And on this picture, any value of the sequence is a height, and anything that you claim is a limit of the sequence is going to be a height. It certainly looks like height 0, just like we were perhaps led to guess with the other picture. Maybe 0 is the limit of those guys. Okay, let me go ahead and cheat a little bit. Just redraw part of the picture for S sub n. That's 1 again. So there we started with a half, and then a half plus a fourth, and plus an eighth, and plus a 16th. You know what? It's going to be really helpful if I just draw a horizontal line at exactly height 1. And what we see is when we keep doing this thing of adding half of what's missing between the current sum and 1, it looks like that horizontal line is going to be perhaps our limit. Okay. So now we've got those pictures, we can do a pictorial version of what we might think the limit is. But let me actually start out. Let me do something else. Yeah, I don't really need that. I can use the room. Okay. So, like the claim would be that the limit as n goes to infinity of, say, the a sub n sequence, just 1 over powers of 2, is equal to 0. And, well, let's just write it out. We also have a claim for s sub n as well. Equals 1. And we'd like to make those claims precise. And yeah, let's do the pictorial version first, even though we want to get to the careful definition. Here's where that second picture is helpful. Although I really like the first picture of just points moving on a number line, but it can be helpful to actually have n explicit. So I'll just recreate almost exactly what I had before. Okay, let's just do this one for right now. Let's put this one up pretty high. Here's a half, here's a quarter, here's an eighth. Okay. And we had these dots going down, 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 to where you almost can't see the difference. Well, you really can't see the difference by the time you get to 7 or 8 or whatever. So we'd like to say informally, and we'll formalize this, informally we'd like to say something like the values of a sub n, which are 1 over 2 to the n, if we want the formula, eventually get arbitrarily close to 0, which we're claiming to be the limit value. And a good picture for that, and it's going to be actually very tied into the explicit definition, is that I focus on this arbitrarily close. I'm not saying that these values get to within a distance 0 of 0, because that would be, say, the values would be equal to 0, and they never are 0. We're saying that they get very, very close to 0. So I need to make this more explicit, and I need to get that eventually. I need to make that more explicit. And you know what? I'm also going to say one more thing. I'm going to say, and they stay there. I'll talk about how we might make a mistake if we don't emphasize that as well. So let's just focus first on the arbitrarily close bit. And this is one of the absolute key things about limits, is that we have to choose temporarily what we mean by arbitrarily close. So I'm going to just say, let's say I just want to get it within like basically sort of 1 decimal place. Let me put in like 1/10 right here. I'm just going to put a little band. Let's see, that will work. I'm going to go give myself a little wiggle room between minus 1/10 and 1/10, and I'm going to see, do the terms of this sequence actually get within that amount of wiggle room, that definition of closeness, to the claimed limit 0. And in fact, they do. After first few terms that aren't anywhere close to 0, they get close. 1/16 is less than 1/10, 1/32, 1/64, 1 over 1/28. Those are all between minus 1/10 and 1/10. So to the person who's not particularly interested in amazing accuracy, that's looking good. these values are getting close enough to 0. And one important thing, to stay there a bit, is suppose I had something that the dots went under 1/10 and then occasionally, but repeatedly, like had these blips going up, and then small, small, small blip, small, small, small blip, small, small, small blip. Even though most of the values were really close to 0, if it repeatedly keeps jumping out of this band, this error tolerance, that's one way to talk about it, then we wouldn't really want to say that the limit is going to be equal to 0. Even this person, who's pretty vague and pretty undemanding about accuracy, can see that they would refuse to say the limit is going to be 0. So, good place to stop this video. I don't want to make each one too long, but this picture is going to be really key. The idea of picking something that we think is a limit value and putting an error bar or some sort of band or error tolerance around it and seeing if the dots get inside that bar.